to climate change, and not only to increasing temperatures and changes in precipitation patterns, but particularly also in changes in the probability of local climate extremes. Moreover, tropical mountain forests are particularly threatened by deforestation, which we have heard this morning already. And already in 2008, the lowlands of the province here in the south was already deforested by roughly 50%. So projections of these very complex and biodiversity-rich ecosystems are a challenge, and the current approaches comprise, for instance, revisitations. Here, the famous first assessment of Alexander von Humboldt in 1802 was reassessed in 2012, and they found that vegetation moved upslope by 500 meters in roughly 200 years, which is one approach to look how biodiversity patterns change. Another approach is to use scenarios, and here in this example, the proportion of natural forest cover was first of all depicted using remote sensing data, and then different scenarios, either considering only socioeconomic indicators, which is the purple line down here, then deforestation would increase dramatically, or considering also biodiversity and ecosystem indicators, which is the blue line, which will kind of decelerate deforestation loss. Yet, as I showed you, it's difficult to project these biodiverse ecosystems, and for that, trait-based approach or concept have been proposed as an opportunity kind of to get an insight on the mechanisms that drive changes in species communities, how they respond to abiotic drivers, but also how they feedback because of, for instance, changes with future communities with species, some kind of increase, as we've heard also by Carlos Ivan, others decrease, and maybe these changes in the community composition, particularly also based on traits, may kind of change and have a feedback also on the ecosystem, and that's why these trait-based approach can quantify species interaction and ecosystem functions. Also at that time, traits have been integrated into models, into land surface models, and mostly based on global databases. So here, for instance, the specific leaf area was used to look at changes in or how drought affects Amazonian biomass production, and you can see here that while biomass was soon achieved, the same measure of biomass was achieved after disturbance, they could show that there's a change in the SLA classes. So still, these models currently rely mostly on global data and are mostly based on a few plant functional types, for instance, in tropical mountains. And moreover, they do not consider biotic interaction nor the interactions of the biosphere with the atmosphere. And that's where our endeavor started 4.5 years ago. We had the aim to unveil how ecosystem biomass production and water fluxes as major important ecosystem services here for Ecuador are affected by climate change and land use change through alterations in response and effect traits. And for that, we had the aim to look at on the one side, to look at traits and use an adapted response effect framework. And the second point is the biodiversity land surface model, which includes local trait data and also modules for biotic processes. So in general, our framework is comprised of 4 major elements. First of all, we collect intensive field data on joint plots. We use these field data both on abiotics, biotics, and interactions in the response effect framework. We then use these data and also what we've learned here in a biodiversity land surface model. And we do have, due to the long research that has taken place here, also independent field data to assess how good our models project what we see in the field. So you have seen already, or many of you know many of these faces, and many of you are sitting here. So we are an interdisciplinary consortium based on experts in modeling scenarios and abiotic drivers, and also on functional traits and biotic processes. And of course, as has been strengthened today, we have we have many different Ecuadorian universities and collaborators which are essential for our project that range from Loja over Cuenca to Quito, and also, of course, comprise our partners, our local partners here that run the 2 stations, Nature Culture International. And you've heard already during the last symposium, which took place in October 2019, that we started working, or we are working for a long time in the mountain rainforest along the elevation and gradient from 1,000 to 3,000 meters. And in the second phase, we now extended our work to the dry forest. And this is particularly interesting, not only because the elevational gradient then increases from 600 to 3,000 meters, but also because of the seasonality that has been mentioned by Carlos Ivan already. So what we did is, on the one hand, working from 1,000 to 3,000 meters in natural forests and pastures, we collected a lot of abiotic drivers, functional traits such as the specific leaf area, and also biotic processes, and so that we can model target function in the end and have a lot of wealth of data in the mountain rainforest, and are currently in the process of collecting such data in the dry forest. There we have a similar design working from 600 to 1,000 meters, again in natural forest and the replacement system, and we also collect trait data on tree species that cover the whole spectrum from deciduous to evergreen species. So I will now only show some highlight results or appetizers, because all the other projects will present their data in detail. So what we could show, for instance, for the mountain rainforest is that regarding the trait-based response effect framework, that mean annual temperature is having an indirect effect, similar as you have seen this morning in these structural equation models, through the specific leaf area on the net primary production above ground. But if we look then, for instance, using similar data on herbivory, we see that not temperature and precipitation are most important, but it's rather the relationship, the phylogenetic relationship of the different tree species. But again, this modulates the effect through traits such as specific leaf area, but also secondary compounds in the leaves. And to get a better and a more holistic idea on these patterns, how environmental heterogeneity, such as precipitation, temperature, and soil parameters shape the role of diversity for ecosystem function. We currently compile data both from Ecuador and Tanzania on species richness and also species turnover for different processes, which you see in the next slide. And what we could show that not only the diversity of species that is in a system is important for the diversity effect on functioning, but also the species turnover, which shows that the identity and particularly also the traits are important for the functioning of these ecosystems. And this pattern was similar across the 2 mountain systems, and shows that kind of it's not only biodiversity, but particularly also the identity, which is important. And for that, we looked at biomass stocks and process rates. So we looked how many birds are in a system, how many ants, or how much seeds get dispersed. And we could show for Ecuador and for Tanzania both that species richness and species turnover is important. If all the dots are on the right side, you see a positive effect of diversity for ecosystem functioning. And you see that in both ecosystem and along the elevation and gradients, both matter, diversity and identity. The second major point of respect is to biodiversify land surface model, and for that to then project environmental change effects on the target function, biomass production and water fluxes. And for that endeavor, the modelers developed the so-called new model, or a mixture of different models, which you see on the next slide. Humboldt, which stands for Hydro-Atmo Unified Model of Biotic Interactions, Organic Matter and Local Trait Diversity. And instead of developing a new model, the 3 modeling groups coupled 3 different models. So the LPJ guess, which has its strengths in dynamic vegetation composition and detailed structure. The climate land model, which has a close energy balance and detailed energy fluxes between the biosphere and the atmosphere, and the catchment model framework, which considers particularly the multiple soil layers, the detailed water fluxes, and the detailed soil representation. And these three models regularly interchange their parameters, so the meteorological and hydrological parameters from the CLM and the CMF are calculated on in a 5-minute basis, while the vegetation data is calculated on a daily basis. And so they interchange their variables. And then I stated earlier that we need more trait diversity, also considering the fluxes between the biosphere and the atmosphere. And for that, we measured the radiation partitioning across for more than 100 tree species. And what you can see here is that there are roughly 8 different classes of, for the 100 tree species that differ in the partitioning of radiation. And therefore, this also shows that considering trait diversity in these models is particularly important also to better predict or project the fluxes between the biosphere and the atmosphere. We are in the lucky position that there's a lot of data on the tree species in the mountain rainforest available, so we could replace these 8 different or 12 different plant functional types with which we worked a priori by a trait continuum and their variability. And you can see here that a lot of traits are strongly correlated with one another, like the leaf CN ratio or the specific leaf area. So in the end, the key traits for the models are specific leaf area and wood-specific gravity. And they have been implemented now in the Humboldt model. And not only the trait diversity of the trees, but also soil nutrients have been implemented in the model. And you can see here exemplary for the netto primary production. On the one hand, okay, these gray bars are not well visible, so that's the measured data, and the colored plots are the simulations. And what you have to trust me now is that the model that includes the traits and the nutrients performs much better than the ones where either the nutrient limitation is not included or the trait variation is not included. So we have a strong improvement to project netto primary production by using both trait diversity and nutrient limitation. We then, as I said, have also independent data that can be used to test the model, and here we use the ecovariance data on the pastures, and what you can see here by the comparison of the different models, so the atmosphere model alone or the different coupling until the Humboldt, that the Humboldt best predicts latent heat flux on the pastures. You can also see that the measured and the model heat flux do differ. We kind of predict the heat flux by the model, and this is most likely the case because also the plant functional types on the pasture are not the same as in the forest, and so there needs to be improvement. The other independent data we aim to use is remote sensing data, or we currently use already, to come from the leaf scale to the tree and then the plot and later the catchment scale. And for that, we already used, for instance, Landsat data and SLA or other leaf properties, and it could be shown that they, at least at the plot scale, were very well or very useful to upscale the data that we measured on the leaf scale. And this is a promising start for the overall endeavor of respect the area-wide implementation of the model, where we then aim to come on a grid scale of 1 kilometer resolution. And for that, we will then have simulated data from the model and observed data from remote sensing, and hope to be able to project across the catchments, both in the rainforest and in the dry forest. And if this works well, we will then be able also to use scenarios, both on climate change but also on land use change, and project how these different ecosystems will respond to climate change, and also develop optimized land use scenarios that mitigate climate change effects. So the take-home message for RESPECT as an overall framework is that I hope that I convinced you that trade-based response effect framework and the biodiversity-informed land surface model will improve our mechanistical understanding of the interplay between drivers, traits, processes, and ecosystem functions, that we will be able to upscale from the local ecosystem to the catchment ecosystem through remote sensing and modeling, and with this also be able to test scenarios for climate and land use change and make area-wide projections for ecosystem resistance. And with that, I'd like to thank you. You will hear in the following talks more insights on the different sub-projects, and if you're interested, you find our newsletter from late last year on the webpage, and of course also more information and all the published data, at least the metadata and the publications. So thank you very much. And
we want to thank you, Nina, for excellent overview, excellent presentation, and use of time. It still remains 3 minutes. Maybe if somebody wants to make a question, are welcome. If no, let's talk for the next one. Okay. Yeah. We want to invite Professor Katia Trachte, who is now working from the Brandenburg University of Technology, Cottbus, Sanftenberg. She will today show some very special presentation about the analysis atmospherics for CO2 and H2O atmospheric fluxes above the canopy in the mountain, the dry forest in Laipuna Reserve. Please give your welcome to Katia.
Thanks, Balthasar, for the introduction. I'm here today to present results from a PhD student, Charuta. She unfortunately cannot be here to present her results so far for herself. So we are working with atmospheric carbon and water fluxes in the rainforest and also in the dry forest, and the results today will be focusing on then the dry forest. So when we talk about the dry forest in Laipuna, then we know, and we heard about it this morning, that the climate is then strongly driven by the seasonality, driven by the atmospheric circulations. And particularly this seasonality also then affects the biosphere-atmosphere interactions. And the question is, how can we then identify these impacts, these alterations on the exchange processes? And for this, we have then indicators for these feedback effects. One indicator are the microclimatological conditions, and for this, we use the basic then variables as relative humidity and temperature, but also to go more into detail then the heat energy budget, and also then the water availability, and that means water in the soil and the precipitation. And an additional indicator, and that is particularly our focus, are the atmospheric water and carbon fluxes. And the processes behind are then the evapotranspiration and biomass production, so our target functions in the RESPECT research unit. And what we try, or what we aim to disentangle then are to understand the role of the mountain dry forest and its seasonality in the sequestration of and storage of carbon as a contribution to climate change mitigation. So CO2 is a strong greenhouse gas, and the amount of evapotranspiration, and also we aim to disentangle then the environmental drivers of carbon sink and sources, particularly in the seasonal cycle. How do we do this? We use the ecovariance measurement technique, and so it is a direct measurement technique to obtain the water and carbon concentration in the atmosphere, and then derive the flux directions. And so, as you can see on the pictures, we installed a new ecovariance station then in the Laipuna Mountain Dry Forest in April 2020. We equipped the tower with then an open path measurement system, and also then with typical biometeorological sensors as temperature, relative humidity, precipitation, and net radiation. We also moved then our ecovariance station from the pasture system here in the rainforest in October 2020 to Laipuna, but since the period is very short, we focus only on then the forest ecosystem. Yeah, so since the canopy of the mountain dry forest is less dense than here in the rainforest, we additionally, but non-continuous, measure then the soil CO2 efflux to then catch the contribution of the soil to the CO2 signal we measure then with above the canopy. And at the last point, we also do some drone or analyze some drone imagery to obtain then area-wide information of the vegetation for the footprint analysis. So the approach is then, if we measure the atmospheric carbon and water concentration to derive then net ecosystem exchange, that means to derive then the flux direction, and so with this we can then determine the evapotranspiration. That means, for example, as you can see here, if we have more upward than downward transport, we know that we have a flux into the atmosphere, and that means evapotranspiration, and the same is true then for the carbon dioxide biomass production if flux is more directed downwards. Nonetheless, we have the net ecosystem exchange then, and we need then to partition this net ecosystem exchange into its gross components. That means the gross primary productivity, GPP, and ecosystem respiration. That means we have to partition then the balance between both, and with the final data, we can then identify cross-scale interaction and feedback effects by means of comparisons between wet and dry season, and with the stations here in the rainforest also then the analysis along land use gradient and the climate gradient. Yeah, so our results so far. So we start with the microclimatological conditions, the basic variables as already mentioned. You can see we start here in April 22, and then the last data set we have so far analyzed is then mid of January 23, and we see we have a clear signal in the relative humidity with the higher values during the rainy season, and then it decreases from approximately 80% in April down to 55% in October, and we also see then the signal in the temperature with a mean temperature around 23, and so with slightly increasing values here during the dry season. I guess what is more interesting is then the water availability in the system. So we analyzed this by means of the precipitation and the soil moisture, where we then catch a direct signal and dependency on both. And we see that we have over our entire period we analyzed so far have a total precipitation amount of 148 millimeters, and then with the highest value of around 90 millimeters then in April, and then we have the dry season, and then the precipitation is then increasing again from December. We have a direct response to the precipitation in the soil moisture, so high soil moisture than in the rainy season, and it is decreasing almost to zero in the dry season, and then it will increase further during the rainy season. Yeah, below on the second figure, you see then the evapotranspiration in gray, and then the water vapor pressure deficit. Again, two variables interrelating with each other, and we see the same signal that we have the highest evapotranspiration rates during the wet season, and then it is decreasing by approximately 50%, and during the same time then we have the increase of the water vapor pressure deficit, and so as a response to the dry atmosphere. Yeah, so to go more into detail, we take a look at then the heat energy fluxes and the water and carbon fluxes along then our time series. And here you can see then the monthly mean diurnal cycle of sensible and latent heat flux. The sensible heat flux in gray, and the latent heat flux then here in black. And we see the typical then diurnal cycle month per month. And so what is obvious that the sensible heat flux is the dominant heat flux in the system, except for April. So there is a clear balance between latent and sensible, but then it clearly changes. And so usually the ground heat flux, which is shown here in red, is below the latent heat flux, but here in the system, due to the dryness, we see that even in the dry season, then the ground heat flux here in red is stronger than the latent heat flux. Yeah? And so that is clearly then the response to the lack of water availability in the soil, and the lack of foliage, of course, of the forest. When we now go to our water and carbon concentrations in the atmosphere, again, we can see that we have a clear seasonal cycle with the highest amount then in April. So what you can see is the carbon dioxide concentrations of the atmosphere in green, and the water concentration then in blue. And so it is decreasing. That means the atmospheric water following the seasonal cycle as the carbon dioxide as a response to the loss of foliage, and then it is increasing towards the end then here of the year and the beginning of the wet season. And so what is interesting as well is that we have here the typical diurnal cycle with this inverse signal, the high water concentration during daytime, and then the lower concentration of carbon dioxide during daytime as well, and so as a signal of photosynthesis in the system. And this signal is then changing towards the dry season, and I showed this here in this lower figure as well, where we compare then April and August to then have the opposite months, the wet month in the wet season and the months in the dry season, and there we see that the amplitude is then particularly changing. So that means we have a typical inverse diurnal cycle from April to June, characterizing carbon uptake and water loss due to photosynthesis, and this signal is then changing in the dry season. Yeah, so What we can see here is then finally the biomass production of the system, or the quantification of the biomass production of the system. So you see here NEEs, the net ecosystem exchange, and the partitioning into the into GPP and R-eco. So if we see here then NEE, that is in gray, starting again in April, and so it's negative. Negative NEE means the transport toward the land surface. So remember, we are measuring in the atmosphere. That means a loss of carbon to the atmosphere and gain to the land surface. So then that means negative values towards the surface and vice versa. And then this NEE is partitioned into GPP, that is the bright red color, and the respiration here in dark red. And then what can we do with this balancing of the partition values? We can quantify and determine then if the system is a carbon sink or a carbon source, and that means if then the ecosystem contributes to climate change mitigation, or if it contributes to a higher concentration of CO2 in the atmosphere. So again, and of course that is not a surprise, we see the typical seasonal cycle in NEE and its partition values, with the highest amount then in April and May. We know then due to the foliage and photosynthesis, and what we are interested in is then the amount of carbon sink, the amount of GPP, and we can quantify then during the wet season a mean gross primary productivity of GPP of 250 gram carbon per square meter and month, and in comparison then to the respiration means we have a higher value of GPP than respiration, and that means during the rainy season we have a carbon sink. That means the ecosystem takes up more carbon, and if we then go into the dry season, as you can see here, then we see that the gross primary productivity is of course decreasing, and we can quantify that it is decreasing down to 50 gram carbon per square meter times month. And if we follow then both lines, then we see it is clearly balanced between then the respiration and the productivity, and that means during then the dry season we have more or less a balance between carbon uptake and carbon release, and this is of course as well not a surprise due to the loss of foliage then during this time. And we can then quantify the differences, and that means we have a reduction of GPP by 80% due to the loss of foliage from the wet season to then the dry season. And with this I come on to the take-home message. Our results so far, or the first analysis so far of the eddy covariance data showed promising results. And so we can demonstrate the ability to quantify water and carbon fluxes of the mountain dry forest, particularly the seasonal cycle. And so we can state that the mountain dry forest is largely controlled by the amount of water availability in the ecosystem, and that's driven by the atmospheric circulation. So we have a clear cross-scale interrelation between then the carbon cycle, the carbon sequestration of the system, and then the the superordinate atmospheric circulation. We have a clear response of biometeorological parameters to the changes in the ecosystem, and that is the reduction of evapotranspiration, soil moisture, and relative humidity. and the increase in VPD. And that is the wet and dry seasons showed a clear impact on the carbon sequestration capacity. And then what we are, our next steps are then to go more into detail, particularly then with the contribution of the soil carbon efflux and the impact of climatic stress on net ecosystem exchange and evapotranspiration, and also then the transition between the wet to the dry season and then to the wet season and again. But yeah, I'm convinced we will then present these results next week in the symposium. Thanks for your attention. And of course, thanks to all team members who makes this work possible.
Carbon and water fluxes is an excellent topic. Please, I would like to ask if there is any questions. If no, we want to thank you, Katia, for excellent presentation. In order to continue the schedule, we have to small switch in the programmation, and we want to invite for the next one, Professor Wolfgang Wilke. Oliver is not coming? Oliver is not coming? Yeah. Yeah. Professor Wolfgang belongs to the Institute of Geography and Geology for Karlsruhe Institute of Technology. And today he will explain and talk about drivers of nutrient supply in Andean forest.
Okay, good afternoon all together. I'm a bit surprised because there was somebody else announced, so I have to improvise a little bit. I will talk about nutrients. Nutrients are important for biomass production, usually in a way that the more nutrients there are, the more biomass is produced. But nutrients are also important for species richness. In the reverse way, the more nutrients there are, the less species occur together. Therefore, if you want to understand global change effects in our study forests, we need to know which of the usually 4 nutrient supply processes are relevant. All ecosystems, including our tropical montane forests, receive nutrients by mineral weathering, nitrogen fixation, a biological process that oxidizes atmospheric nitrogen, organic matter mineralization. This process releases inorganic nitrogen, ammonium nitrate from the organic matter, and deposition from the atmosphere, input from the atmosphere. All these processes are susceptible to environmental change. They respond in a certain way to climate change, for example. And therefore, we need to know which of these 4 processes that occur in all ecosystems are the more relevant one for our study ecosystem. On the other hand, if you want to study global change effects, we can do this by permanent observations, or we do it by space for time substitution, and in respect, we are following both approaches. We have a long-term observation site now exactly for 25 years, and we use a space for time substitution approach. I can use this. Our aims today, or my aims today, are to talk about the weathering rates for mineral nutrients, to assess the role of different end sources, particularly of nitrogen fixation, determine mineralization rates, and finally assess the role of nutrient deposition. So we are looking into all these 4 nutrient supply processes that occur in ecosystems, and we focus on the humid part, at 1,000 to 3,000 meters above sea level. The site should now be well known. It's the famous tropical montane forest between Loja and Zamora, on the rim of the Amazon basin, so on the humid part of the eastern Cordillera. And there's our long-term ecosystem study, and there is the joint core plot design of the research unit. And you've seen this graph already, a bit smaller, so now it's back again, a bit larger. And I would like to cut it in the middle because we are only looking today at the natural forests. In our long-term ecosystem study, you can see it here on the right-hand side. It's a small catchment, about 10 hectares large, between about 1,900 meters above sea level and 2,200, perhaps 150. It's fully covered by tropical montane rainforest, receives about 2,500 millimeters of precipitation, and is drained by a single stream in the middle of the catchment. You can see here is the stream bed. We are collecting since 1998 all ecosystem fluxes that are relevant in forest ecosystems. So we start with the rainfall, and we do not only measure the water fluxes, but also the solutes in the water, and therefore we call it bulk deposition. Then we estimate dry deposition to get the full input. Then we go into the system, collect throughfall, stem flow, a little bit of water is running down the stems. We measure litter fall. Then we go into the soil, we measure water and nutrient fluxes through the thick organic layers, the O horizons, with a litter leachate sampler. Then we have soil solutions from A and B horizon, have determined weathering release, and sample the stream water. So we fully cover the waterway from the atmosphere through the whole system to the stream. This allows us to budget the various ecosystem compartments, like the canopy. There we can come up with a canopy budget, we can budget the organic layer, and we can budget the mineral topsoil. So let's come to the first results. The first thing we did, we determined weathering rates with 3 different methods. I will not explain the details, but what you can easily figure out on this graph is the weathering. The weathering is these blue bars, and you have really to look closely, and then you detect, okay, there are a few small bars. They are much smaller than the nutrient released by mineralization, and these are the red and the green bars. These are just 2 different approaches to measure nutrient mineralization by dividing the stock in the organic layer through the litter fall, or by doing incubation experiments. These mineralization processes are by far the most important nutrient supply processes in the system. For nitrogen, you don't see any bar in blue because nitrogen is usually originating from the atmosphere. So this result shows us that mineral weathering is only relevant as nutrient supply process in the long term. These mineral nutrients accumulate in the system. They're also important in very young ecosystems at early succession states, but they are less important in the long run. Let's go to the second question. Which role does the nitrogen fixation play? A common approach to assess this question is to measure stable nitrogen isotope ratios. Stable nitrogen isotope ratios are expressed as differences to internationally accepted standards. And the standard for nitrogen is the air. And because the air is the standard, it has a delta 15N value of 0 per mil. If now the nitrogen originates from the air, the nitrogen in the ecosystem should have a delta 15N value close to 0, close to that of the atmosphere. So what can you see in this graph? we have these nice blue rhombi, and we have red dots. The blue rhombi are the soil solutions, are not the soil, the ecosystem solutions, including soil solution. We again go through the system: rainfall, throughfall, stem flow, literature is here, soil solution at 15, at 30 centimeter depth, and stream flow. And the red dots, these are the solid materials, like the leaves, like the organic layer itself, like the A and the B horizons. And we have differentiated the organic layer into the three horizons that commonly occur: a little degraded OI horizon, more degraded OE, and fully decomposed OA horizon, and the roots. So, and if you now only look at the closeness of our diverse red and blue dots to this zero line, you figure immediately out that most of our solutions and solid phases are far away from zero. There's only one exception, and that's stem flow, interestingly. The first conclusion I would draw is nitrogen fixation does not play a major role in nutrient supply for our ecosystem, but in stem flow, there might be a contribution. Perhaps the bark is a nitrogen-poor habitat, and there could be, for example, cyanobacteria that can fix nitrogen there. Interesting question to follow. Small detail, not important at all. Okay, let's go on. I've already said organic matter mineralization, which is the release of nutrients, inorganic nutrients, by decomposition of the organic matter, which is done by microorganisms mainly, but before microorganisms can take over, usually some shredding is necessary by soil animals. We can study nitrogen mineralization in different ways, and one way I also mentioned already is to run incubation experiments, and these incubation experiments can be done in the lab, then they are rather artificial, or in the field, then they are more realistic, but usually we can only do it for short term. So we did short-term field incubations using soil-filled cylinders, which were inserted in the top mineral soil, the uppermost 10 centimeter, and left these cylinders for 1 month in the field. And these are the results. And the results are indeed unexpected. Because we would have thought with the increasing elevation, the climate gets worse, wetter, cooler. This is usually something microorganisms don't like, and therefore we thought we should have found decreasing mineralization rates with increasing elevation. Surprisingly, the reverse is true. Then we thought, okay, it's 31 days, it's a month, perhaps there was good weather in Cajanuma and bad weather in San Francisco. Perhaps it's just an artifact. But to check this, we then continued and used another approach. This other approach is related to the fact that with increasing soil depth, here you can see such a soil, a bit small, but this is a soil. This is the surface, and then we go into the soil deeper and deeper, until 60 centimeters in this case. And in such soils, we usually find that the carbon concentration decreases with increasing soil depths because the input decreases. And then we look at another isotope system, the carbon isotopes. Again, same story. These isotope ratios are presented as differences to international standards. For carbon isotopes, the international standards is PD belemnite. This is a fossil, does not exist anymore, I think, but the first people who measured delta 13C values used it. They had it just available, and now everybody in the world just does it. So it's not a meaningful standard. Okay, but the delta 13C values, they tell us stories. For example, with increasing soil depth, the carbon concentrations decrease, but the degree of degradation increases. The deeper we go into the soil, the older the organic matter, becomes, that can also be dated, and the more decomposed it is. And the decomposition is related with the release of CO2, and this CO2 is isotopically light. So this contains more 12 carbon than 13 carbon, which is typical for any kinetic fractionation process. Therefore, the delta 30C value increases with steps. The organic matter gets heavy with steps. So, and if we now calculate a regression line of the delta 30C values on the carbon concentrations, log transformed, we get a slope, a typical simple regression line with a slope. And this slope is indicative of the long-term degradation of the organic matter. And then we use this slope, usually it's called beta, it's also something somebody decided a long time ago, and if we correlate this value with our short-term incubation, we find a close correlation, which means the explanation that there was good weather in Carranuma and bad weather in San Francisco does not hold. Obviously, mineralization increases with increasing elevation. We cannot yet explain this fully, but the results are rather stable. There was another not so big surprise here. Here you see the metasediments. We only have one metasedimentary plot at 1,000 meters. The others are all metasediments. At 1,000 meters, otherwise the granodiorite dominates, and the granodiorite sites show a much lower mineralization rate, which means that you really need to consider parent materials when talking about ecological processes. So let's come to the final part. The fourth input of nutrients, the fourth supply mechanism is the deposition from the atmosphere, just the nitrogen and the phosphorus that drops from heaven. And as you can see here in blue, this is the nitrogen from 1998 to 2019. We can see an increase. It's almost a doubling if you look at the regression line, or there's some temporal variation, but there are enormous inputs. For phosphorus, this is the red graph here, we don't see an increase, but we see a lot of spikes. So there are occasions when a lot of phosphorus arrives in the system. And the interesting thing is, if we look first at the lower part, both the nitrogen and the phosphorus do not leave the topsoil, the mineral topsoil. So everything is retained in the ecosystem, which of course means that the ecosystem becomes increasingly nutrient-rich. For nitrogen, we find a net loss from the organic layer, but already an accumulation for phosphorus. With this, I come to the end with a few conclusions. I think you have seen that mineral weathering is slow and ecologically only relevant in the long run, so it is not, it's not important when considering changing nutrient availability in response to global change. Nitrogen fixation from the atmosphere also does not play an important role. It's not really a surprise because our system is rather nitrogen rich. Also, still nitrogen plus phosphorus limited. The important process is the nitrogen mineralization, or the mineralization process does not only deliver nitrogen in the soil solution, but also all other mineral nutrients. And there we have some surprises seen, increasing mineralization with increasing elevation, which is unexpected, big difference between different parent materials. So this is something we have not yet fully understood. Furthermore, the deposition is important, and the interesting thing is anything that drops from heaven is kept in the system, and the system gets increasingly nutrient richer. It accumulates nitrogen phosphorus, and what we can see is that as the third most important element, potassium, becomes increasingly important, is more and more retained in the system. There was it already, thank you very much for your attention. I thank a lot, a million of co-workers. It's 25 years. I exploited a lot of students, really a lot of them. Got a lot of money from the DFG, and the Ecuadorian authorities allowed me to do it. So thank you very much.
Thank you, Wolfgang. Thank you. I think we have no time for questions. We are on time. Thank you. You would like to invite the next one, explanation. Thank you very much. Excellent presentation. We would like to invite Dr. Dantas de Paula. He's here. We will talk about the modeling the present and future of Ecuador mountains and dry forests. Dantas de Paula, doctoris, belongs to the Department of Physical Geography from Goethe University, Frankfurt, Maine.
Okay, many thanks. Happy to be here in Ecuador. So I'll be presenting the sub-project A4, which is related to the vegetation modeling part of the RESPECT project. So, yeah. Exactly what do I mean by models, right? So there are several types of models in ecology. We have no models and so on and so on. But the specific type of model which I'm referring to here is the dynamic vegetation model. So dynamic vegetation models, they are basically computer programs which simulate the dynamics, the growth, the death of trees and vegetation and so on, plant individuals. And they're used for estimating the future or the structure of forests, because obviously trees, they grow and die very slowly and so on. We cannot do very common kind of experiment then. So here's an example. We take data from the field. We represent the trees as simple simulated constructs, right? The simple stems and crowns, so on. And then here, there's a publication which was done by a group before us, which simulated the landslides in Ecuador. Okay. And exactly where we are, the A4. So we are included in the part A of the sub-projects, the modeling scenarios. And we have two major groups there. And we are, the four is composed by me and Thomas Hickler. So the objective of the A4 group is basically to develop a vegetation model that's able to simulate this gradient of structure and biodiversity in the tropical forest of Ecuador. So you see again this very nice image here, but on my side I transformed all of the pretty real trees into pretty fake trees now for 1,000, 2,000, and 3,000 meters. And why is it interesting to model, I would say? So basically, every time something is hard to do on the field, or maybe it's impossible to measure or impossible to estimate, we do a simulation experiment for this. So it's an interesting niche for dynamic vegetation models. And also, we interact with several of the other sub-projects. So for example, we interact with A1, plant traits, we get from them the trade-offs and so on, data, driver data from all of the other abiotic variables, for example, and so on and so on. So it's a very interesting position to be in because we get to interact with all of them and learn a huge amount of information of how these forests work and so on and so on. So what we actually did to include biodiversity in the dynamic vegetation model. So the concept is the plant traits, of course. We don't deal with species exactly, but we deal with functional diversity. So the plants or species as a whole, they have differences between them, and these differences, they lead to the different traits for specific parts of their organs, for example. So leaves, for example, they can be very hard or very soft. Wood, the same. Roots can then become very thin or very thick and so on. And then these differences, they determine the strategy of the individual in order to deal with differences in the environment, which means that we can group these strategies into two different main groups. So we can have the conservatives, which are the ones who conserve their resources. And we have the acquisitives, which are the ones which actually don't conserve, but they actually want to spend more and grow as fast as they can, so on and so on. So in order to simulate, we started with an already existing model, the LPJ gas, which is an interesting model which combines vegetation dynamics and soil organic matter dynamics, which is very relevant, as you would see very soon, for this tropical ecosystem. And then, of course, the vegetation interacts with the organic matter, throwing its leaves and so on. The leaves decompose, become available nitrogen and phosphorus, which then the individuals take up again, closing the cycle. And what we did, actually, we created a trait variation model, which determines the capacity of the individuals to capture more or less nitrogen and phosphorus, and if they need more or less of it in order to survive. So we did this also by using a lot of field data, a lot of information from the other groups, especially the B1, the plant traits, which you'll hear more about in a short while from Jürgen Hohmeier. So in the blue squares in the middle here, as you see, we have here the variables which are the most randomized with an establishment. When the individual is born, it receives one value of leaf, of a specific leaf area, which determines if the leaf is going to be soft or hard, conservative or acquisitive. Also receives a value related to the wood, it's going to be hard or not, and receives a value of the roots if it's going to diverge or not. From the leaves, we can estimate how much they will need in terms of nitrogen or phosphorus. We can also estimate the longevity of the leaf. If the leaf is very soft, it will live very shortly. If the leaf is very hard, it will live longer. And from the wood, we can determine if the tree is going to be a very soft wood, going to die very easily, or if it's going to be a hard wood, it's going to die harder. So there's the mortality rate of the individual. And from the roots, it determines if the root is going to be able to acquire its nutrients all by itself, or if it's going to pay a part of its carbon to a companion mycorrhiza, which will help it to acquire nutrients from the soil. The green here are data from the field, directly from our sites in the RESPECT project, and the red ones are data that were collected from the TRI database, global values, which were not collected from us. So here you can see how these field measurements compare when you compare the 1,000, 2,000, 3,000 meters. How do they look like? So the temperature, it goes down with elevation from 19 to 9.4 degrees on average per year. The precipitation does not change so much, a little bit more in the highest elevation. The biomass goes down from around 150 to 80. The NPP also goes down, the productivity, and the SLA also goes down. So the trees become more conservative as they go up in elevation. They have harder leaves going up, they have harder wood going up, and they combine better with mycorrhiza, and they have thicker roots as they go up the elevation. So let's run the model now, and as you can see, every little point here that you see on the right side is one individual tree. So we start from a bare ground, and this tree starts growing and competing with one another, and then what emerges out of this is the community of trees which the environment shapes. So if this here was a model without trait diversity, it would have only one point right in the middle here of its graph. But this is a diverse model. You can see all of these individuals competing and everything being filtered on the side. So this is something very new for this region, and we can actually now simulate biodiversity in a much more realistic way. Yeah, so what does this mean? Now let's do some experiments with this model. So I will highlight very quickly here two of the experiments that we did. We have many others which we are working on. So we wanted actually to see how nutrient availability is important for shaping this community around this gradient. Because as we see here before, on the last line here, I mean, temperature changes, of course, precipitation changes, but the soil available nitrogen for plant growth, it goes up a bit here, but then it goes down to 2. So many of us researching on the field have theorized that the main reason for this change in biodiversity and traits and structure is due to the change in nitrogen availability. Now we can test this with the model. We have a publication that we've done together with subgroups A1, subgroup B1, and the A3, those are dynamic nutrients. And then we have here the results, which again are a little bit hard to see because it was the same slide we showed before. But as you can see here, here is the model with nutrient limitation, and here's the model without the nutrient limitation. And you can see here, right? Here are the field data, it's here, here, and here. And if we turn off nutrient limitation, if we let the trees grow as much as they want, what happens actually is that the biomass really goes down on the model. So the wood density becomes very soft everywhere because they all converge into this acquisitive strategy. So this is what happens. So we are not able to simulate the forest without nutrient limitation and this organic matter cycle that I showed before. And the productivity, of course, goes up here, much higher than what we expect from the field data over here, and especially, of course, for the higher elevations. Makes no sense. So we have to include nutrient limitation. And so we see the distribution of traits now. Here in blue are the data, field data, and if we turn on nutrient limitation, the specific leaf area fits much better. Here are the averages. Much better with the field data, as you can see here. If we turn off, as you see in the green, all of the individuals, they will shift towards the acquisitive kind of strategy. The same for wood-specific gravity. If we turn on nutrient limitation, it fits on the blue, very good. And if we turn it off, then what becomes filtered is all in these softwoods. And that's why we have this very low biomass. And the second experiment I want to show is, okay, now we know that nutrient is important. What is happening now, which was shown by, before by Wolfgang Wilke here, what will happen if the nutrient deposition goes up in this area due to anthropogenic nitrogen deposition? Let's see what's going to happen. So I'm not talking about climate change by what we knew before, temperature and so on, but now climate change or environmental change due to nutrient deposition. So here's the data that was showed earlier, but only on dissolved inorganic nitrogen. There was an increase. This was measured on the field by the subgroup A3. So we know that it's increasing on San Francisco, on the tropical mountain forest. But where does this nitrogen come from? So they have this other paper here which shows, using remote sensing and measurements, that this end deposition has come from the increased fires in the Amazon. So this is a direct effect of change, especially in Brazil, and is affecting here all of the tropical mountain forests of Ecuador. So you can look at this paper in more detail if you want. They're very interesting here. So with this data, we created a scenario of nutrient decrease going from the year 2000. We have here the field data, and then we use data from the ACC MIP project, which has projected for the future, how is it would increase, and then we fix historically for before the year 2000, before the increase. And then we apply this scenario here of increasing nitrogen deposition on the model, and let's see what happens now. So obviously we can see that there's a huge amount of increase in productivity due to this deposition of nitrogen coming from the Amazon fires. You see here in the green line here what would happen if it did not have until the year 2100, and what would happen here with the nitrogen with the increase in deposition. So all of our measured sites, they increase significantly in the model. And of course, most importantly, specific leaf area and wood specific gravity, so leaf softness and wood hardness, they become higher, the specific leaf area increases and the wood becomes softer, which means that all of the individuals, they become more acquisitive with this increased nutrient deposition. So we have a significant shift in the community here due to this increased nitrogen deposition, which of course is a huge problem. So besides that, we are working on other experiments together with other subgroups from the RESPECT project with the B4, where we found out that including herbivory does not impact the nutrient balance and also not the carbon balance of the forest yet, but we're still working to see what would happen with the mountain dry forest. Also with the B1, we also included this root rate variation to see what happens with the mycorrhiza and how important are mycorrhiza for this environment. Yeah. And with the B3, we are also planning to include reproductive traits, the seed size and so on, to see how this will change with the elevation. And lastly, of course, which was already cited here, we are working on the coupling of the LPG gas entity, the Humboldt model, and create this coupled version, which would also improve the fit of the model to observations. And then, of the phase 2, of course, we are very excited to go into now to the dry forest sites and work with this completely different environment, which not only has the difference from elevation on the spatial scale, we have also the difference in the temporal scale too, from rainy to dry areas. So we also want that this, now we have to include hydraulics in the model and a response to drought and how we were going to deal with deciduousness in the model and biodiversity, of course, in order to reproduce what's going to be measured in the field. So now I think you have some interesting results relating to how does functional diversity change with these climate change. And so this model can really, maybe in the future, give you an answer of how functional diversity can help us protect against climate change and so on. See if the system is more resilient, for example. No? So, yeah, we are working on now on the hydraulics, exciting, waiting for the results. And yeah, I think looking forward to the next use of the project. Many thanks.
Thank you, Matthews. Thank you. Continue with the schedule. We would like to invite Professor Thomas Knoke, who is coming from the Technische Universität of München. And we will talk now very interesting topic too, deforestation process and deforestation trajectories, new approach to model of this.
Good afternoon. I'm very happy that I finally arrived and can give a talk here. But I have to announce that what is now between you and the coffee break is another model. It is a deforestation model. That sounds a bit ugly, but still it is important, because if we would like to control deforestation, we must understand it. We must see what are the drivers. Is it mostly market-based or other non-market-based drivers? And that will be the topic today. I have to thank Carla for helping me to make the presentation a bit more beautiful and for the Spanish. Yeah, then just let's start. Before I go more into the details of the topic, let me first introduce you in the inspiring world of decision theory. Decision theory broadly subdivides model types into normative models, predicting what the people should do, that are cool models, can help us to improve, but can never be tested because nobody does what he or she should do. And the other type of model are the descriptive models, more dealing with what people really do. For example, statistical models, how farmers would diversify their land use, or how maybe land use trajectories would develop under maybe purely perspective of farmers. We have developed already quite a lot of models with the help of our Ecuadorian partners, but what we did not do so far is that we consider that the farmers and decision makers are so heterogeneous. And for this, we have now developed a new model which is stochastic, and this model considers that farmers are heterogeneous and they have different expectations, and we try to consider this in our new approach. The mission today is that we would like to try to model purely market-driven deforestation decisions, because for any assessment you need always a baseline, a business-as-usual scenario, and we here define as business as usual the purely market-oriented deforestation. It is of practical importance. Of course, we will also need this for then to develop future land use scenarios, but also looking back, we can see whether it was possible at all to control a little bit deforestation, or whether we have to be desperate about this topic that deforestation can never be stopped. So policies or governmental changes can be evaluated when I compare this business as usual with the observed deforestation. That is what we will look into a bit more in detail. The model looks a bit complicated, but the essence is that we established 100 heterogeneous farmer groups per each year of our observation. And then these farmers, they try to become more happy. They reduce their dissatisfaction with the current land allocation. That is a basic idea. We developed also some measures, how we can measure this dissatisfaction. But I think the time is not enough to explain it more in detail. Farmers are heterogeneous. We look at historical data, but we could also use, and we will use, data of the process-based model. Productivities, for example, are now historical, and prices as well. And the farmer expectations, they are heterogeneous and simulated by random processes. So the method is we apply Monte Carlo simulation and then subsequent optimization, several runs. And we integrated for the Ecuadorian example 1.5 million profit scenarios, and for the development of the model even 9 million profit scenarios. So first of all, how does the model work? We developed the model on the basis of Brazil, Congo, and Indonesia. They account for 45% of the world's deforestation. We see that the model is robust. 2 independent model runs give consistent results. And when we compare predicted and observed deforestation using a statistical model, we get quite satisfactory results with 75%. A poor economist is happy about 75%. That is, for us, is good. But of course, who cares about Indonesia if we are here in beautiful Ecuador? We applied this approach also to Ecuador, but I must admit that the results are a bit surprising for me. Maybe you can help me to interpret the results. So this graph is now the main outcome. Here the x-axis is a timeline. The y-axis is the forest loss in 1,000 hectares. So here the 95 means 95,000 hectares forest loss. These gray diamonds is FAO statistics data. The magenta line is our model. And the blue line here, that is observed deforestation. That is this global forest watch data, which is, I have to admit, is a bit, for me, unexpectedly low. But it is a commonly referred data set, and I think Jörg can later tell better if the quality is high enough, but it is the only consistent data I so far found We have also different results, and we must discuss this. So what can we see now? We took the first 5 years of the FAO data, and then we calibrated the model. So we could not come closer than this, on average, 80,000 to 95,000. That was good enough for us. But then when we further simulated, the model had an own dynamic. For example, it followed quite nicely declining crop revenues by declining deforestation. But then when we had this tortilla crisis with the increased crop returns and prices, we have elevated deforestation. And then we had again declining, and at the end, after 2010, we have quite a good fit of the modeled deforestation and the expected. Keep in mind, the modeled is totally independent of the empirical deforestation. It is only artificial, only market-based. So what has happened, 2000, we had the dollarization and the governmental change. From 2006 onwards, there was another change, and environmental movement was strong. 2008, we had Socio-Bosque, and the constitution included even own rights for nature. And I don't know whether this is the reason why we have here, from the perspective of a market-oriented farmer, unexpectedly low deforestation. So if we accept these results, we can now look how many hectares of forest we have saved, and we can assess this then. For example, we could look how much more carbon would we have emitted if this market-based deforestation would have taken place, and we can then look how much social costs have we saved. Social costs of climate change are sea level rise, more energy, we have higher mortality, and agriculture suffers also. And this is then, this is only methods detail. We were a bit lazy. We simulated always 5 repetitions with the same market data and the same landscape and land use context. So we have always to look at these clusters of 5, but I think that is only methods detail. What we then tried to find out, what is the monetary benefit of the reduced deforestation if we accept that there has been a reduced deforestation. We can see here that from 2002 onwards, that are the green bars, so this is a lower emission than expected, and here we have the CO2 equivalents in million megagrams. That constitutes, through avoided damages, a social value that are the reddish bars here. And the US dollar values are here. You see that are also large numbers. We even could account for that this effect is not permanent. So that after this period we evaluated, we have a 1% chance of losing all the saved carbon. Still, we have then a positive effect. If we exclude this risk of reversion, the value of the benefits is $3.2 billion US dollar. If we include it, it's still 1.8 billion. The loss, so the net benefits foregone by farmers, is only half the size than the benefits by the climate benefits we can achieve. I mean, it is very tentative, of course. We can a lot discuss about this, but I find this also an exciting approach to evaluate whether we have achieved something in the past or not. What is the future? I think the model, from my perspective, works, but now the further work has to be done by Carla and Jonathan. They have to calibrate the model for lower spatial scales for regions in Ecuador, our 2 regions, for example, make the predictions spatially explicit, set up mountain dry forest model, that is Jonathan's mission. So still a lot of things are to do, and we have to include also some normative elements. How can we improve the land use? By including important functions such as water and carbon. Yeah, sorry for my little bit jet-lagged presentation, but I'm now at an end, and maybe it is allowed to have one question or so. Thanks a lot. But if the time is over, it's over. question is always a bit disappointing, but it is. So everybody wants the coffee, I can understand. Jörg.
Well.
Okay, this widely accepted data of deforestation, which data that were they this also the lower curve? Was it, oh, it's not anymore there.
This blue curve?
Yeah.
That was tree cover loss by Global Forest Watch, and the definition, I think, is stand replacement event on 30 by 30 pixel.
And did you compare that with the works from Ecuador? So is it right what they are doing?
This is especially for Ecuador, but I did not compare it with your studies. Your studies were a bit opposite. I think they had an increasing deforestation, and therefore I admitted that this is tentative. But if we accept this Hansen data, I think then there's still some hope that we can achieve something. Okay.
A question not only to you, but also to our Ecuadorian hosts in the room. I thought that grazing would be one of the main drivers of deforestation around here, or clearing the forest for grazing. You didn't mention livestock. Or maybe I'm wrong.
Yeah,
grazing
yeah.
is not
I mean,
so important.
I was a bit superficial. I mean, the model always considers 7 land use types, and the competitors of forests are expanding by this market-oriented land allocation, and pasture is the main driver in this model. But also, of course, banana and so is also included. So as far as we could, we tried to make it as realistic as possible.
Thank you, Thomas. And yeah, please give him your applauses for favor. And we would like to invite for a next coffee break, please. We have only 15 minutes to continue in the schedule, please. The coffee breaks. 15? Yeah, because, no, it was your fault. See you in 15 minutes. Hola. Invitamos por favor a pasar al salón para continuar con las siguientes presentaciones. Kindly, we ask to... Yeah. Carlita, cerramos las puertas.
¿Está bien desde aquí del podio o quieren? Estamos bien.
Okay. The next presentation is in charge our guest, Dr. Jürgen Homaya, Faculty of Research Management from University of Göttingen. He will talk about the tree species richness and forest dynamics of southern Ecuador.
Welcome back after the coffee break. I hope you are ready for another round of presentations. So I will start to talk about tree species richness and forest dynamics of the permanent plots within our RESPECT design. So after 2 modeling talks, we are coming back to real measured data from the field. You know already the study sites. It's a dry forest close to the border with Peru, and then the elevational gradient along the wet forests from 1,000 to 3,000 meters. And you have seen already this picture showing again the different sites, and like Matthäus and Wolfgang, I will stay with the forest plots. So only the plots here at the left. And okay, that's a short slide about our measures. So what we did was we established in total 15 forest plots of 1 hectare each. Within these plots, there are in total 12,000 tree stems with a diameter of at least 10 centimeters. So the data I'm going to present are based on these permanent plots, on the first inventory that was done for the wet forest plots between 2018 and 2019, and then a remeasurement about 3 years later in the wet forest plots, and also the first inventory of the dry forest plots that was done recently 1 year ago. What we did was we measured all diameters of all trees, we measured all heights of all trees, then we tried to identify all tree species. So the first part of my presentation is about forest structure, about dynamics. The second part is more interesting for botanists, so it's about tree species composition, family composition, and so on. Okay, and in addition, I will present some few figures on terrestrial laser scanning. Last year, we had the opportunity with a colleague from Göttingen to do terrestrial laser scanning in all of the 15 plots. So the first slide, colorful slide. It's only to show you the figure, the type of figure I will use to present you the structural data. So you see here on the left the dry forest sites, on the x-axis the estimated annual precipitation, on the y-axis the elevation of the plots. So at the left you have here the 600-meter site at Laipuna, and then the 1,200-meter site at Laipuna, and then the 3 evergreen moist forests at 1,000, 2,000, and 3,000 meters. So from very hot to colder situations, from very dry to wetter situations. So let's start with the first parameter on forest structure. That's stem density per hectare. And you can see how these are the numbers, the number of stems per hectare. And you can see there is a relation, a strong decrease from our driest end of plot at 600 meters. We have a very low density with about 360 stems per hectare to more than 1,000 stems per hectare at the coldest, most humid sites. So there is a relationship to climate and between climate and stem density. The next figure shows the maximum height that we find in the trees of the plots, and you see trees and the dry forest do not reach more than 20 meters. That's very similar to the 3,000 meter sites, but the highest, the tallest trees are at the lower elevations in the humid forest, so in the pre-montane and the montane sites. Next parameter is canopy openness. That's one result from the terrestrial laser scanning. And again, there is a strong relationship. The more open plots at 600 meter in the dry forest have about 20% of canopy openness. And then that is followed by the 3,000 meter humid site with 15% of openness. The smallest values are found in the pre-montane and montane humid sites, so only 8% of canopy openness. Next parameter is tree basal area, so the total sum of all basal areas of the individual trees. And highest values we find here at 2,000 meter in the humid forest, about 38 square meters of basal area per hectare on average. The values for the dry forest and for the forest at 1,000 meter under humid conditions are very similar. At 3,000 meter, it's a bit higher. So that's a short characterization of forest structure of the 5 sites. For forest dynamics, I can only show you data on the humid sites because we still had no re-inventory for the dry forest sites. So what you see here are the annual rates for basal area growth, for annual stem mortality and annual recruitment. In the light green, the 1,000 meter site, the pre-montane humid forest, and the montane forest site, and the upper montane forest site. And there is a decrease in basal area growth with elevation. You see that mortality is a little bit higher at the lower elevations. The same is true for recruitment. Recruitment rates are a bit higher at lower elevations. So in general, a slight decrease in dynamics with elevation. And then the absolute values, because these are percentages, and this is an absolute change in annual basal area in square meters per hectare, comparing again the 3 sites. On the left, in green, dark green, and blue, the growth and recruitment, so the total sum of productivity, of basal area productivity, and in brown or orange, the mortality. And you see here, values at 2,000 meters are a bit higher, so the values are, the productivity, at least in terms of basal area, is a bit higher at 2,000 meters, and then at 1,000 and 3,000, more or less the same. At all 3 sites, mortality is lower than productivity. So that means we find a net basal area increase at all elevations. If you are wondering because of this effect, this is still basal area. What is missing is above ground biomass. So when we take into account the tree height, probably the pattern will change a little bit because trees are taller at 1,000 meters, so there's probably a bit more of above ground biomass increment compared to 2,000 meters. So now we are coming to species composition and richness. The first slide shows the same 5 sites with an average of tree species that were recorded within 1 hectare. You see very low species richness at 600 meters in the dry forest, about 17 species on average per hectare. That's increasing to 121 species per hectare at 2,000 meters. So that's the average. The plot with the highest number of species had about 160 species per hectare. That's a real high value for 2,000 meters, probably a world record. But again, the pattern, there's quite a difference between the study sites. So in general, the dry sites are poor in species and the humid sites have many more species. Another interesting parameter is the SSCI, this is a Stand Structural Complexity Index, another index derived from the terrestrial laser scanning, and that shows you that we find the highest value for stand structure complexity again in the in the lower montane and in the pre-montane forest, whereas the dry forest sites and the upper montane forest sites are very similar in their structural complexity. So now I'm coming to species, and I will show you different levels of tree composition, starting with the family level. You see here again the 5 different sites, starting at the dry forest site at 600 meter, 1,200, and then the moist forest at 1,000, 2,000, and 3,000, with their total number of families. So you have here the total numbers from 14 families at 600 to 60 families at 2,000 meters. And then the different fluxes show you the shared number of families between the different sites. So for example, 2,000 meter shares a lot of its tree families with 3,000 meters and also with 1,000 meters. And this line represents families which are only present at that elevation. So a lot of shared tree families between the different sites. I will show you some of the very common or typical families for each site. So again, the total number of families per site, and then the most common families. For example, at 3,000 meters, we have the melostomes, with 15 species, the same number of species in the melostomes at 2,000 meters, and they are also quite common at 1,000 meters. Other typical families are the Rubiaceae at the uppermost elevations, Lauraceae at 2,000 and 1,000 meters. That's a very common pattern for montane forests at these elevations. If we look at the dry forests, they are quite different. So the most common family are the Fabaceae. That is shared with 1,000 meters. It's in the moist forests. And then we have some typical dry forest components like the Malvaceae and Caparaceae. So that's quite common, and they are quite different in family composition compared to the humid forest sites. And another feature, this is a representative one, it's Ipomea species, and you see it's wind dispersed, and that's quite common in the dry forest species. So now the next level, we are coming to the genera. This is a genus distribution. In total, we recorded 208 different tree genera within our plots, and you see the same patterns. At 2,000 meters, many genera are shared with 3,000 and with 1,000 meters, but more genera are only found at this specific elevation compared to the families. And that's true for all elevation levels. And if you look at the dry forest, so the uppermost dry forest area is sharing some of the genera with 2,000 and 3,000 meters, but the lowermost level is only sharing most of it with 1,200 in the dry forest, and only I think it's only one genus that is shared with humid forests. So next slide, the tree species. At the tree species level, it's quite different. So most of the species stay at their elevation level. There's quite a few exchange between the elevations and less exchange between the dry forest and the humid forest. So in total, we have here about 105 species in the 3 hectares of forest, more than 200 species at 2,000 meters and 150 species at 1,000 meters. In comparison, only 24 and 40 species in the dry forests. So a short summary on these results from our hectare plots. There are significant changes in forest structure with temperature and rainfall that could be expected. Tallest trees, highest basal area is present in the humid forest at pre-montane and lower montane elevation. If you look at dynamics, we find relatively low growth, mortality, and recruitment rates compared to other sites at similar elevations on more fertile soils, normally the dynamic rates could be double, but values between 1 and 3% are quite common in montane forests. So, as I mentioned before, the rates have to be calculated for biomass. So, the estimation of biomass, including tree height, will change a bit the pattern between the elevations because the tallest trees are at 1,000 meters. Tree composition, yeah, as shown, the communities are very rich in species, especially the moist forests. They have a high structural complexity at the mid and lower elevation in moist forests. Richness is decreasing from dry to humid sites, and with elevation, or the 2,000 meter site in humid forest is exceptionally rich in species, and it's still not quite clear why it is so rich in species compared to the 1,000 meter sites. Most families are shared between the compared study sites, but in species it's not so common that they occur at different study sites. So these data are the basis to use them later for our functional trait studies. So for each of the plots, which are divided into subplots, we now are continuing to gather functional traits. For each of the 500 tree species, we will get the functional traits, and then later the idea is to explain patterns in forest structure and also productivity with functional composition. Thank you very much for your attention.
Hello. Just on time. Yeah, just
What was the idea?
applause again for the very just. Thank you, Jürgen. Maybe there are some questions. We have one.
Thanks, Jürgen. Is it typical also for other montane forests that the species that are shared across the elevations are so few? Do you know that?
I have no idea. So far, I did not compare it to other forests. What we know is that the families which are present in the montane forest, that are the typical families present or common in all montane forests across the Andes.
Perhaps it's more a comment, but it was interesting that the Fabaceae showed up on the poor granodiorite soils at Bomboscaro.
They are not related to soil quality, more to elevation or to temperature. So that's typical that they are common in the lowlands and then reaching up to, let's say, 1,000, some of them up to 2,000 meters, but not more. And for dry forests, it's very, very common that Fabaceae are the most species-rich family.
Well, I think it is also related to the nitrogen availability. It fits perfectly.
Yeah, but they are also quite common on more fertile volcanic soils in northern Ecuador.
But then they do not fix nitrogen.
We don't know. We don't know, Wolfgang.
Yeah, there's a lot of things not known.
We'd like to invite the next guest, Dr. Achim Breuning. From University of Bayreuth, Achim Breuning belongs to the Faculty of Biology, Chemistry, and Geoscience.
Thank you very much for the kind introduction. Actually, I'm from the University of Erlangen, but I have to replace here other colleagues, Professor Beck from University of Bayreuth, who unfortunately was unable to attend this meeting. We are the sub-project B2, and I'm talking today about a collaborative study that we did together with colleagues from the research team of Katja Trachte, and during my talk I will refer to her speech from the afternoon. We were interested to study in more detail the hydrological cycle of the tropical mountain rainforest, and I want to especially emphasize the nocturnal transpiration during the nighttime, where I think we found some quite interesting aspects. If we are looking into the hydrological cycle, we can study it on different spatial scales. Of course, if we are interested in the landscape level, if we want to balance the hydrological budget of the whole ecosystem, that's of great importance, but it's also relevant to know at the individual tree level which species is contributing to which ratio, and finally for process-based understanding, what are the drivers of evapotranspiration, for example. We should also address the leaf level, because that's where all the physiological processes are going on. At each scale, we have to use different methods to study the relevant scales. So at the tree level, we are working with so-called porometers that measure the gas exchange, the CO2 uptake, the water release, the transpiration. On the tree and stem level, we measure the circumference changes with so-called electronic dendrometers at 30-minute intervals, and the subflux rates with Granier elements, whereas, as Katja Trachte perfectly explained earlier, on the ecosystem level, the fluxes are quantified with eddy covariance systems. So in the following slides, you will also always see in the upper right corner these images representing on which of the spatial scales the respective results have been obtained. So let's start with the ecosystem level, and let's first compare the average evapotranspiration to the average temperature measured over 1 year from November to 2019 to October 2020. And what you see here, the red line is the midday line, is that actually evapotranspiration does not follow precisely the curves of daily temperature. Well, from a physiological process understanding, you might expect that evapotranspiration closely follows the temperature. However, this is not the case, because the maximum evapotranspiration rates are always found before the midday. So obviously, a big part of evapotranspiration is not just controlled by temperature, but actively by evaporation by the plants, by the biosphere. If we compare these long-term means with the relatively dry period that happened between the first 3 weeks of August 2020, we can see that absolute evapotranspiration was a bit higher during the dry period, which is not really surprising, but I want to draw your attention to these small red boxes here, because this is the nighttime transpiration, the nocturnal transpiration that was considerably increased in the dry month compared to the long-term mean. If we quantify this, we see that annual precipitation in the ecosystem about 2,000 millimeters per year, whereas the monthly rainfall of this dry August was below 30 millimeters. Under normal conditions, about 80% of the annual precipitation goes into evapotranspiration, whereas evapotranspiration was more than fourfold the rainfall during that dry period. And interestingly, daytime evapotranspiration contributes to about 85% under average conditions, 15% during the night, but this nighttime share strongly increases by about a third during the dry conditions of August. To better understand that, we should go from the ecosystem to the individual tree level. And again, these two graphs show you the vapor pressure deficit of the atmosphere, the long-term mean, again, compared with this dry August. In all cases, mostly the VPD stays below 1 kilopascal, which is actually not a very strong driver for evapotranspiration. And probably as a result, the mean or the maximum daily water consumption measured as sap flux of most of the tree species was comparatively moderate. It ranged between 13, which is admittedly relatively low, to maximum 70 liters per day. Well, that is about 10 to 20% of the evapotranspiration rate that temperate trees can actually conduct. So our first preliminary conclusion is that it is not the individual transpiration rate of different species that drives the high evapotranspiration of the ecosystem, but it's the really close density of vegetation that matters. From this conclusion, the next question arises, are there specific tree functional types or groups of species that have a special contribution to this nighttime transpiration? And here I show you an example of sap flux rates measured over 2 daily cycles from 9 different tree species. In the background is a little bit faint. In gray, you see the vapor pressure deficit of the atmosphere, and of course it follows closely these day and night rhythms. Looking closer to the sap flux rates of the different tree species, it is obvious that we can distinguish different groups. Well, in general, we can observe that during daytime, most of the sap flux, of course, follows the VPD, but interestingly, during nighttime, there's still about 15% of the daily sap flux. So, looking more closely, we could distinguish 2 ecological groups of tree species. So if we draw a line here, we find about 4 of the 9 species with very high daily sap flux rates and very large diurnal amplitudes of sap flux behavior. We call this the Tapirira group. It contains Tapirira, Miconia, Balschmidia, and Wismia, and according to their water relations, which is also called hydricity, we would call this group water spenders, or as it's usually called in the international literature, the anisohydric group of trees. In contrast, there's another group containing 5 species which seem to have a very conservative water use strategy. They are water savers, or called isohydric, and they are maybe represented by Ocotea, the tree species. Let's also look here at the quantitative numbers for the anisohydric group. Interestingly, we find relatively high maximum sap flux rates, however, with a high daily amplitude, as I said, and at the same time, these tree species have a very or relatively high mean leaf water potential. In contrast, the isohydric trees have a relatively low leaf water condension and potential, and also a low total daily sap flux amount. So these 2 types, ecological types of trees, can be clearly distinguished. Now let's look at the leaf level. What are the physiological processes behind? Again, you see here 2 daily cycles of gas fluxes, and I put here Tapirira and Ocotea as the representatives of the 2 different ecological types of trees. During night times, which are here the blue bars in the background, of course there is no carbon sequestration because there is no light, no photosynthesis. However, if you compare here the leaf water conductance and the transpiration of the 2 species, we see that Tapirira, in contrast to Ocotea, has a considerable nighttime evapotranspiration. As soon as there is a certain vapor pressure deficit of the atmosphere, the stomata of Tapirira seem to open and the tree starts to transpire. So it's the stomatal behavior that finally forces the nighttime evapotranspiration, and since the isohydric trees close their stomata at night, it's definitely the group of unisohydric tree species that drives the nighttime evapotranspiration of this ecosystem. You can see it here in the direct comparison. That's a function of leaf water conductance expressed as G in millimole per square meter and second as a function of the logarithm of vapor pressure deficit. And in Ocotea, there's basically no conductivity at a certain low level of vapor pressure deficit, whereas Tapirira, the isohydric tree, opens the stomata and transpires. That brings us to the next ecological question. Is there any advantage for the unisohydric trees to open their stomata at night and transpire? So do these different hydricity types have any difference in tree growth? And so we move back from the leaf to the individual tree level, where we measured here the stem circumference changes. You see again several daily cycles measured in the humid July 2019, before that dry period. And you see as soon as vapor pressure deficit, the gray areas in the background increase, the stems, they decrease their diameter. This is normal. This is not very specific. What is specific is that, again, the group of unisohydric trees represented here by Vismia, Miconia, and Tapirira, the black, the blue, and the orange line, they have a higher amplitude of stem diameter variations, and if there are good growing conditions, they grow faster than the isohydric trees. So that's what we conclude. The unisohydric trees show stronger stem circumference changes, but also higher growth rates. And one hypothesis behind might be that this continuous water flux from the soil is increasing the nutrient content of the trees. However, Jürgen's group once measured the nutrient contents in leaf and found no difference in isohydric and unisohydric tree species. However, it could be that these nutrients are not stored in some tissues but directly invested in stem growth. That's a hypothesis that may have to be tested. I want to draw some general conclusions. I hope I could convince you that it's worth to look at different spatial scales to come to a better or a more complete understanding about the hydrological budget of the landscape. So definitely to quantify it on the landscape level, we need eddy covariance, or let's say we need to quantify the water fluxes on the landscape level to understand the balances of the ecosystem, but it's very worth to look at the individual tree species. On the one hand, this is relevant for the biodiversity of the ecosystem. If we simulate what climate change might, how climate change might influence the water balance, it is very relevant to know at what degree of change individual tree species drop out of the system and how the balance of isohydric and unisohydric species changes. Finally, to understand the physiological processes that are directly driven by the environmental parameters, it's important to look at the very small spatial scale. The story I just told you was just accepted by publication in PLOS ONE, and by tomorrow, 31st of March, you can access this paper online on the website of PLOS. Having said this, I want to acknowledge the help and cooperation of many colleagues here in the room and outside, of course, financing by the DFG, the support from NCI and the Ministerio del Ambiente, and last not least, I thank you for your kind attention. Muchas gracias.
Thank you so much, Professor Achim Breuning. Maybe if there is some questions, welcome. If no, of course, we want to send our best regards to Professor Erwin Beck. So, yeah. The next guest would like to invite to PhD candidate Lea Keva. She belongs to the second Biodiversity and Climate Research Center, and she will talk about the biotic and abiotic filters of plants.
Yeah, there we go. Hi everyone, yeah, I'm Lea. I'm still a PhD candidate of Eike Neuschulz and Matthias Schleuning, but also collaborating with Carlos Ivan here from the UTPL. And I'm working on the effects of biotic and abiotic filters on plant regeneration. But now, we're in the second phase of the project, my work is mainly, or only conducted in the dry forest in Laipuna. So what I am doing is fairly similar to what a colleague has been done here at San Francisco Station, but now we moved it to the dry forest. So just for you to recall quickly how our study site looks like, this is a picture from November. You can see it's fairly dry, except for a small region where there has been watering been done. And as has been mentioned before, we have two elevations that we're comparing, 600 meters and 1,200 meters. And then we have always three forest plots and 3 agroforest plots on our sites. And I'm conducting my project across all of those plots. First, maybe let's think a little bit about the life cycle of a plant. So for an adult tree to establish in a plant community, there have to be several steps conducted successfully. So at first, the adult tree is producing seeds that then have to be dispersed. This can either be happening passively, for example, through wind, or actively through frugivorous birds or other animals. And then different biotic and abiotic filters at the arrival site determine whether the seed is actually able to germinate and then also grow into a more mature seedling, and finally, from the seedling stage, reach a mature tree or shrub or herb state level. While my colleague Andrea is mainly working on the bird community and the seed rain, I am focusing on the second half of this plant life cycle, and I'm taking a closer look at the seedling recruitment. And I want to understand how biotic and abiotic filters may influence the seedling recruitment and shape seedling communities. So, as you've heard already before, especially in the dry forest, water availability is a very crucial factor to see how, or for plants to establish, especially seedlings. So that's why I'm considering the litter amount to be an important biotic filter, and shade to be an important abiotic filter on seedling recruitment, as both of those factors may influence soil moisture and thus water availability for the seedling. So for the first chapter of my PhD, I'm conducting a seed sowing experiment where we want to test those two filters, shade and litter amount. And I've been sowing 8 different native tree species to the Laipuna dry forest. and we're conducting those for treatment. So of course we have a control, and then I have a litter removal treatment where once a week the litter is being removed. Then we have a shade application. It's a shading cloth, a little roof above the plot, and then we have the combination of both. And this is how this looks like more or less in real life. So you can neatly see the shading roofs, and then we have little metal meshes that protected our seeds in the beginning so they wouldn't be eaten by rodents, for example, right in the beginning. I've been conducting 2 rounds of sowing. So first 4 species that have been fruiting at the end of the rainy season, which is Albizia multiflora, Vocera graviolens, Acacia macracantha, and Erythrina velutina. And then in a second round in December, I've been sowing 4 species that were fruiting during the dry season, which you can see here below. And those species were selected due to their different plant functional types. So some of them are semi-deciduous and others are completely deciduous. And then also according to their seed sizes, as you can see, they vary. As we expect seed sizes also to influence in the recruitment. I'm currently conducting my second sampling round in Laipuna, and this is more or less how one of those sowing plots looks like right now. So here, for example, you can see the seedlings of Erythrina velutina that have already been growing bigger than the meshes even. And I've almost managed to check all the plots, and so far I have roughly 4,400 seedlings measured, which is quite a lot, and we're very happy about this. Still, I cannot really tell yet, because I haven't looked deeper into the data, whether actually the treatments are influencing or not. This is to come. But I can already say a little bit about how the different species are working out in a way. So from the first sowing, Vocera graviolens has not been germinating very well. I have found about 3 seedlings across all my sites, which is not that much. While Acacia macracantha and Albizia multiflora have produced quite some seedlings, and especially Erythrina velutina is working out very well, and I have a lot of them. While for the second sowing, I have 3 species that are performing quite well, and only Cochlospermum vitifolium has not been producing so many seedlings. But how exactly do we quantify if, like, the growth of the seedlings, for example? So I'm checking different parameters on my seedlings, which is one, the height. Then we're also counting the amount of leaves. I'm checking for herbivory or signs of drought. And of course, I'm also taking pictures for identification. And then to account a little for the environmental differences between our sites, we're measuring soil moisture with every sampling round. I have small eye buttons that are measuring the soil surface temperature roughly every 4 hours. And we're also taking canopy pictures, and there's no picture of this, but we're also assessing the litter depth. So this is not all of my project, but the second part for the second chapter is then to also take a look at the natural recruitment that we can find in the dry forest. And therefore I have established 18 plots within every of the core plots, the big ones that we have. And in the beginning, as you can maybe see here, those plots have been completely cleared from seedlings and saplings. And now I'm monitoring what is coming back over a period of a year. Therefore, I'm focusing only on the identification of woody species, as herbs and grasses are just too difficult. I have not been able to measure this round, so this is still pending, and I'm very curious to see how it looks like. For the last part, we hope that since those experiments have been already conducted in a pretty similar way here in San Francisco, that we will be able to compare my findings in the dry forest to the mountain rainforest. Let's see how that goes. To give you a brief outlook, because I cannot show you so many results yet, so I'm currently in my second sampling round. I'll be here again, June, July for the third round, where then the first part of the sowing and the natural recruitment will be completed, as they always run for an entire year. And then I'm coming back again in November to finish the second sampling, so that this one will also have an entire year of growth. And then my results are to come, and hopefully when we meet up again for the next symposium, I can show you some more about this. Maybe last but not least, of course, I'm not able to do all of this by myself, and I thank very much all of the people that are helping me, especially the two from Kangoraka, from the village close, that are conducting all of my treatments, which especially in the rain season is great work. And then Cleva and Diana helping with the measurements in every sample round, and also Jonas, who's been joining this time to help out. And now, thank you for your attention, and if you have any questions, please feel free.
Okay, many thanks, Leah. If there is some questions, please, welcome. If no, I would like to present our next guest, Nina Farvik. Nina belongs to the Department of Biology, Conservation, Ecology. He will talk about the patterns of arthropod communities, herbivory, and predation in a mountain dry forest, southern Ecuador. Welcome, Nina.
Yeah, thank you, Balthasar. I'm the last step before the poster presentation, the book presentation. I'm in charge today because Anna-Marie can't travel at the moment, and Roland and I are just doing kind of the organizational part, and most of the others did all the work that you will see in the slides now. And there will be also two posters that you can see in the next poster session, one by Camilo and one by Diana. So arthropods are the most diverse group of animals, and they kind of strongly shape vegetation patterns, structures, and composition. And it has, for instance, been shown that also not only the vegetation structure and composition, but particularly also the nutrient fluxes are strongly influenced, whether they are herbivores present or whether they are present or whether they are no present. So there's much more flux of nutrients into the soil. And yet, while there are some studies have been carried out on single arthropod species and their role for herbivory of plant species, the patterns at the community level are hardly resolved. So the motivation or aim of our project is to understand how abiotic drivers shape, on the one hand, the arthropod communities, but also kind of the role as herbivores. And also, of course, there are a lot of arthropods that are predators, but we also consider vertebrates in the predation experiments. As you've seen this slide before, we work, as Leah has just mentioned, both in the natural forest and in the agroforest, both at 600 meter above sea level and at 1,200 meters. And we use the same tree species to conduct particularly the palatability experiments and also to assess herbivory as, that have been selected by Jürgen. So to assess predation, we used children toy experiments. So we made lots of these lovely plasticine caterpillars that range from, this is rather red-brownish, so in the next slide it's brown, so don't get confused, to green and white. And these dummies were attached with needles to these leaves and then exposed for 4 days. And then we could, based on the marks that we could find on the different caterpillars, assess which predator was there and was attracted by these dummy caterpillars. So here are the first results. It's preliminary results, not finally sorted, but what we could show or what we could see is that most of the dummies were attacked by arthropods, so roughly 70%. Birds took roughly 20%, mammals and reptiles around 4% each. And if we look a bit more into the arthropods, you see that kind of the largest part of caterpillars were attacked by small ants. There were a lot of crickets and grasshoppers attacking them, and also spiders, big ants, beetles, true bugs, and some unknown arthropods were among the predators. You can see also here that kind of they had a bit of color preference, so brownish. So previous slide you saw it's rather reddish, but it's brownish tone of the Pleistocene were attacked most, followed by the whitish ones, and the greens were attacked least. If you compare then the elevation and land use types, you see that in green here in the forest, we did not find a difference in predator attack on these caterpillar dummies, while with 15%, the attacks on these caterpillars were quite high in the comparative study that we did in the mountain rainforest. We had an attack rate of lower than 10%, and for the pasture or agroforest, we found that the predation rate is higher in the lowlands, while it's lower at 1,200 meters. And though this is not well, you cannot well see this, we found in the mountain rainforest that kind of the predation pressure decreased with elevation, because in these harsh environment at 3,000 meters, we didn't find many arthropods. We then assessed the arthropod community in general, and here you can see Jana, who will give the Spanish talk tomorrow, and they collected the arthropods by beating samples. So you have this white cloth below the shrub where you are beating on from both sides, and then you collect with these sucking tubes all the arthropods and sort them later on. And what we found is that the majority of arthropods we found in the understory were spiders, followed by beetles, but also Isopoda, Hymenoptera, caterpillars, true bugs, cycads, mites, and some others were among them. If we compare the family richness at from 600 to 1,200 meters, we found what we expected, that in the areas where the environment is not so harsh with higher precipitation, we also found a higher family richness there, both in forests and in pastures. And when we look then on the herbivory, or in the first case on the plant palatability, you see here again the three different plant functional types, from deciduous over semi-deciduous to evergreen species. And you see here the leaf area loss that was assessed by feeding trials. So we offered leaf discs of each of the species to 20 centimeter diameter to crickets from Gryllus acillimilis of 22 different tree species. And you can see here that we found a decrease in palatability from the deciduous to the evergreen species, which was also expected. Yet, as the species are distributed across the two different elevations, and we find some, and that's what I maybe have to discuss with Jürgen, we also found a slightly higher palatability based on the distribution of the tree species at 600 meters, and a lower palatability at 1,200 meters, which was quite unexpected, as we would have expected that, particularly in harsh climates, plants invest more in kind of secondary compounds or thickness or toughness of the leaves, so that they can't be eaten so easily. Then we quantified the herbivory of all the leaves that were collected last year in the joint field campaign by Project B1. It was in total of 21 tree species here, and we assessed the leaf area loss then via scans. And what you can see here, the leaf area loss kind of in situ, in the tree crowns where we collected the leaves, there we did not find a difference in the leaf area loss across the three different plant functional types, and the leaf area loss was roughly less than around 7 to 8 percentage. We also compared then the leaf area loss across the two elevations, and you can see here, which is kind of predicted from what we have assessed across all the different species, tree species before, that we did not find a difference in the leaf area loss of the leaves collected from the tree crowns along the elevational gradient. In the next step, we quantified then also the damage types that we found on the leaves that we scanned, and we differentiated 8 different damage types: sucking, piercing, margin feeding. There are also pathogens. You can see some pictures of these different feeding types down here. And you can see that there was a rough or a medium damage type of roughly 4 different damage types across all the 3 different plant functional types. And the damage type diversity did not differ among the 3 plant functional types. And you can see here also in a different visualization that the different feeding types, from garling to surface feeding, also were relatively constant across all the different plant functional types. And so we did not find also in a different multivariate analysis, no difference there. So to sum this up and to conclude, we could show that arthropods are the main predators of Plasticine caterpillars, and again, as in the mountain rainforests, mostly ants left their bite marks at the caterpillars. We found that spiders, beetles, and isopods are the most abundant arthropod orders, and we found a higher richness of arthropod families at 1,200 meters than at 600 meters, which we expected. Oops. And we found that the palatability differs between the 3 different plant functional types, with deciduous tree species being having a higher palatability than the other 2, but herbivory and damage types across the plant functional types and elevation did not differ, and maybe we need to discuss this in more detail. And as I said at the beginning, it was not me doing the field work. I only visited the sites once or twice, but all these people did all the work in the field, Maria Mazon and Roland Brandl are missing on the slide. Thank you very much. Okay, Balthasar is not here, so if you have questions now, we can discuss them now, but maybe we are a bit late, and so we kind of move around this wall and first have a short introduction into a new booklet by Jürgen and Eike, who are in kind of, you will do it here or over there? Here, okay, you will start here. So you will first get a short introduction into the new seed guide that is now available online, and then we move over to the poster presentation, and there we will start today only with the English posters, and tomorrow we have the Spanish posters, so as it was already a long day, so don't make it not longer.
So, good afternoon again. It's a great pleasure for me to present you this new book that was printed last year. It's a field guide of animal dispersed plants, fruits and seeds in and around Podocarpus National Park. It's in Spanish and in English. It presents 40 common species of animal dispersed plants, woody species distributed between 1,000 and 3,000 meters in and around Podocarpus National Park. So this book was mainly compiled by Diana Acosta and by Maciek Bacik, 2 PhD students from the first research phase of RESPECT, and with major support of the local universities, of the UTPL, of the UNL, and also of INABIO. We will have some hard copies during the poster session, and in addition to the hard copies, there's this small card with a QR code, and this QR code should lead you directly to the PDF version of the book. But unfortunately, it seems that it does not work. We checked it recently, and it still did not work. But there's also an online PDF version on the homepage of the Respect group. So feel free to come to our desk if you want to have a look. We have some hard copies available.